Good morning to myself P. Vanitha, working as Assistant Professor, the Department of Electrical and Electronics Engineering. Today we will study the DC to DC buck boost converter. This converter combines the features of both buck and boost converters. It can either increase or decrease the input voltage depending on the duty cycle of the switch. The circuit consists of a switch, diode, inductor, capacitor and load resistor. The switch is usually operated using PWM or pulse width modulation. One important characteristics of the buck boost converter is that the output voltage polarity is opposite to the input voltage polarity. Therefore, it is also called an inverting converter. The duty ratio represented by K is refined as the ratio of on time to the total switching period. By controlling this duty ratio, we can regulate the output voltage. This slide shows some important applications of buck boost converters. They are used in battery powered systems where the battery voltage changes during charging and discharging. They are commonly used in power amplifiers, automotive electronics, DC motor drives, adaptive control systems and self-regulating power supply systems. The ability to both step up and step down voltage makes the buck boost converter highly flexible for renewable energy and portable electronic applications. The buck boost converter operates in two modes. In mode 1, the switch is turned on and the diode is off. During this interval, the input source supplies energy directly to the inductor. The inductor stores energy in its magnetic field. In mode 2, the switch is turned off and the diode becomes forward biased. The stored energy in the inductor is transferred to the load through the diode. The alternate charging and discharging of the inductor enable the converter to regulate the output voltage. This slide shows the important waveforms of the buck boost converter. The first waveform is the PWM gate pulse controlling the switch. The inductor current increases during the on period because energy is being stored. During the off period, the inductor current decreases as energy is delivered to the load. The voltage across the switch and the output voltage also vary according to the switching action. These waveforms helps us understand the converter operation and energy transfer process. During mode 1, the switch is on for a duration of kT. The diode remains reverse biased and does not contact. The source voltage appears across the inductor, causing the inductor current to rise linearly. According to the inductor voltage equation, VL equal to L into DIL by dt. Since the inductor stores energy during this interval, the load receives power mainly from the capacitor. This slide derives the change in inductor current during the on period. The inductor voltage equals the source voltage. By integrating the inductor operation over the on-time interval, we obtain the increase in current. The change in current depends on source voltage, inductance and duty ratio. The expression is later used to derive the voltage conversion ratio of the converter. During mode 2, the switch is turned off. The inductor opposes the sudden decreases in current and reverses its polarity. This forward biases the diode, allowing current to flow to the load. The energy stored in the magnetic field of the inductor is now transferred to the capacitor and load. The inductor current decreases linearly during this interval. To derive the output voltage equation, we apply the volt-second balance principle. The average voltage across the inductor over one complete switching cycle must be 0. Equating the volt-seconds during on and off intervals gives the voltage conversion ratio. The resulting equation is V0 equal to minus K by 1 minus K into Vs. The negative sign indicates that the output voltage polarity is opposite to the output voltage polarity. This equation shows that by changing the duty ratio, the converter can either step up or step down the voltage. The ripple current is the variation in inductor current during each switching cycle. During the on period, current increases, and during the off period, it decreases. The ripple current depends on inductance, switching frequency, source voltage, and duty cycle. Reducing reducing the ripple current, it improves the efficiency, reduces the loss, and increases the converter reliability. Although the capacitor smooth the output voltage, small fluctuations called ripple voltage still exist. Ripple voltage depends on capacitor value, load current, switching frequency, and duty cycle. Increase in the capacitance or switching frequency reduces the ripple voltage. A low ripple voltage results in a more stable and higher quality DC output. In continuous conduction mode, the inductor current never falls to zero. To maintain this operating mode, the inductance and capacitance must be greater than certain critical values. These values are known as critical inductance, critical inductance and critical capacitance. Continuous conduction operation provides better efficiency and smoother current flow. This slide derives the expression for critical inductance and critical capacitance. The derivation is based on maintaining continuous current and limiting voltage ripple. The critical inductance is obtained by equating the ripple current to devise the load current. Similarly, the critical capacitance is obtained from the allowable ripple voltage. The design equations are LCR equal to Vs into R by 2F into V0 minus Vs and CCR equal to K divided by 2 into Fr. These equations help engineers select proper component values during converter design. Thank you.